Okay, any question about the previous session? Previous session, I talked about a situation in to a vector composed of two parts, as we see in the case of bidirectional GAN. We observe that if, for example, z and z theta of z, this is one vector, another vector is e psi of x and x. If marginally z and e psi of x have the same distribution, and x and g theta of z have the same distribution, the complete distribution for the two vectors may not be the same. In this session, I just want to demonstrate it using a simple two-dimensional Gaussian distribution. Before seeing the figure, let's talk about the PDF of a joint distribution, a joint Gaussian distribution. We know that the PDF for a Gaussian vector x with parameter mu and sigma, this is the mean, this is the covariance matrix, equals 1. The PDF over x with parameters mu and sigma equals 1 over 2 pi to the power of d over 2. The absolute value of the determinant of the covariance matrix to the power of 1 over 2 times the exponent of 1 over 2 x minus the mean, the transpose, the covariance matrix inverse x minus mean. Okay? Now assume that each element of x, for example, x1 is the first element of x is coming from a normal distribution with mean mu1 and the variance sigma 1 to the power of 2. And the second element is also coming from a normal distribution with mean mu2 and the variance of sigma 2 to the power of 2. Does it imply that the PDF is fixed? Do you have enough information in these two distributions to form the PDF? Is these four parameters enough to form the above PDF? Yes? Yes or no? No. What is missing? Yeah, the covariance matrix is not complete. Why? We know that the covariance matrix equals the diagonal elements are the variance of each element. It is not missing. Okay, we have this too. The off diagonal element here, is it complete? No. We have a row value here. Let me show you an example. I should open the code. It's not in the slides, it's in the, I have the code. Okay. So just one point that this row value is between 0 and 1. It is between -1 and +1. You can show this property using Cauchy-Schwarz inequality. And thus, based on the value of rho, which can be different values, the joint will be changed. Let's watch some of the examples. This is the code. Sorry for the code presentation. Here I assume that I have a mean, I have a variance, that this is the mean, 1 and 2, the variance is 1 or 3. For 3 different values of correlations, I want to plot the resulting scatter plot of the joints, okay? In the first part, in this part, I plot each of the, let's say, distributions separately, and then in the next part I plot the scatter plot of the joints. All the figures are open on the others. This is the marginal distribution of each of the elements. We know that the marginal distribution is very simple because you know the first element, the mean is 1. The mean of the first one is 1. The variance is also 1. The second one, the mean is 2. The variance is 3. So it is wider in terms of its distribution. But when you scatter plot the joint, this is the result. In all of these 3, the marginal distributions for each of x1 and x2 is the same. There is no difference. All of them are the same as you see before. But based on the correlation value, you see different distributions. So the correlation is very important. It is a simple case of 2-dimensional. When you have 2 vectors of different sizes, for example, in GAN, these 2, it becomes much more important how they are interrelated in the vector. Does it make sense? Okay. Let's continue our discussion about GAN and finish GAN today. Okay. About the GAN, we see different types of GAN, F-GAN, Y-GAN, CycleGAN. And now we just want to conclude the GAN part. Yeah, also the other results of CycleGAN. For example, you have a bunch of horse and bunch of these types, then you can match condition on this input, you can generate this output because you transfer the style of this type of animal into your input. This is different results, and this is the inverse zebra to horse. And also, for example, you have an input and you want to observe the resulting painting if these well-known painters paint the same scene. As you can see, you transfer the style of Monet into this input, Van Gogh to this input, and others. And you see the content is preserved due to the cycle consistency term you add to your loss. but the style is completely transferred. You can find lots of interesting examples in this source. Okay, any question about CycleGAN? Now we want to conclude the GANs and then start the energy-based models. The pros are you can generate high-quality samples using GAN. You see that in the previous methods we do not observe very interesting examples in terms of concept and perception. But using GAN, you will see really interesting images generated from random noise. You have lots of freedom in choosing the generator. Why? Because it is likelihood free. You do not have any consideration about the likelihood or computing the likelihood, anything like that. You just have a model that transfers you from the latent into the observed data. And this can be any model that can provide you with the input and output dimensions. There is no restrictions. You can also work on other ideas, FGAN, YGAN, CycleGAN, and lots of other ideas that are in the literature. And the cons is that you do not have the likelihood calculation. This is a major problem. You know that, for example, in some tasks like outlier detection or out of distribution detection, the likelihood is important calculation that can the generative model provide you. For example, autoregressive models or flu models can have exact likelihood calculation, and it can be very useful in some tasks. But GANs do not have the likelihood calculation, and they are likelihood free. The training is hard due to mode collapse. We see that the mode collapse happened because maybe your generator target or emphasize on one of the peaks of your data, and then other peaks are not covered. As a result, you have samples that are generated, but they are very similar to each other. You do not have diversity in your samples. This is the other problem. And the other deficiency is with monitoring the training. You know, when you have the likelihood based, or even in the case of VAEs, you can monitor the likelihood or a lower bound to the likelihood. But in the GAN, you do not have such things. You may use some inception score or some other metrics that are used for monitoring genetic models and evaluating them, but there is nothing that is aligned with the training. You know, when you train based on the likelihood, you can exactly calculate it on the validation set and monitor what and how the model is performed. But in the GANs, you do not have such metrics. And lots of time you just monitor the generation performance visually, and then you can decide whether the GAN is working very well or not. And also, there is no latent inference in the original setting. We see that the ByGAN can provide you with some latent variables, but latent variable inference, but in the original GAN, you have not such tool. Any question about the GAN? Yes.
What do you mean by the freedom in choosing the generator? Freedom.
It means that you can generate, you can use, for example, in the case of approximate posterior model in a VAE, you are inputting X into a model, but the output of this model is not your sample. It is a mean and covariance matrix. We know that it is diagonal. The covariance matrix, and then it is input to a sampler. And then at the output, you have your sample. You know, and we see that this sampler has lots of problems. For example, reparameterization is just to handle this sampler. But here you have just one generator, and generator is just constrained to input Z from Rn and output X from Rd. Yeah, because of this, you have some freedom in choosing this. But here also you can choose anything. But for example, to generate the covariance matrix, there are lots of constraints. It cannot be. It should be positive definite and something like that. Any question about the GAN? Okay, now we want to switch to a very interesting type of generative models, which is a bit different from what we have seen before. And that's the energy-based models. You will see that your freedom will be totally increased in these models, but you have some problems to be handled. The intuition. Let's start with the intuition of the energy-based model. The target of an energy-based model is to provide you with a network. This network is such that if you input your network with a sample, the network can calculate the likelihood of that sample. Totally different from something like GAN that generates a sample. It generates the likelihood to some extent. It calculates, not generate. It calculates the likelihood. So the network can be arbitrarily different. For example, it can be a CNN, it can be a RNN, it can be transformer, anything. It is constant just to accept X in the input and output the value of the likelihood. You know, this is a very interesting and nice concept, but it causes severe problems. What are the problems? Let's focus on the property of a PDF. We know that a PDF, p theta of X, must satisfy the following two properties. The first one is that the likelihood must be positive. The next one is that the area on the curve or the volume of this model must be equal to 1. If you do not apply this limitation, the model will not work. But it is the property imposed by the PDF. So it seems easy. Again, we can have these types of modeling with the fact that this p theta of X must be positive, and also the integral, the area under curve for this manifold must be equal to 1. Let's think how we can satisfy these two conditions. Okay, the first one is very easy to be satisfied. How? I can assume that I have the model. This model outputs something like e theta, and then I input e theta into an exponent and I know minus e theta. For example, I'm add a minus term to e theta, and the output exponent of minus e theta is always positive. So I satisfy the first condition. So this option is also one of the best options here. You can think of other options. For example, you can make it to the power of 2 and any other types of nonlinearity. For example, like you can pass it through a ReLU nonlinearity, anything like that, and at the output you have something which is not negative. But this option is accepted options in the community because of several reasons. What are those reasons? The first reason, if you have fast variation in the exponent, why we use exponent to make the result positive? Well, the reason is that if you have fast variation in this function, so for example, assume that in your training data there is a place that you observe lots of data here. So your generative model must have a sharp peak here, something like that, okay, when trained, conceptually. This sharp peak necessitates something in the form that you parameterize E. When you use exponent, the sharpness needed in E to generate some curves like this is effectively reduced. We will see a figure in the next slide that provide you with some intuition. Just think that using exponent, you can better model something like this. The next one is that when you use the exponent here, the resulting distributions become similar to a family of distribution functions named exponential family. The exponential family is very well studied in the literature, and they have lots of properties, lots of theorem over them, and you can use all of them after you train your model. So this is the next the next feature that make the exponent one of the best options. And the last one is there is some resemblance between the physics, statistical physics, and this concept of exponent of minus e theta of x. This is not the topic of this course, but this resemblance also provides some intuition to select the exponents. Just to make some more intuition for the first reason, pay attention to this figure. What is this figure? This figure is that you want to provide something like your unnormalized distribution is something like this blue curve, and then using two different types of nonlinearity, for example, the exponent and the power of 2, you want to generate some f theta of x that the resulting exponent of f theta is again your blue curve, or the power of it is your blue curve. As you can see here, the red curve is the most smooth curve. Why is this the most smooth curve? Smoothness can be translated into the changes in the behavior of your curve. As you see here, these two, blue and black, start with 0, and you have some change in their performance here, and also here, and also here. So they have 3 points of behavior change. Okay, does it make sense? At this point, at this point, at this point, they have change of behavior. But for the red curve, you have always something like the previous one. You have some a similar behavior through all the curve. So it is a bit smooth. In the context of, for example, something like Fourier transformation, you can better understand the concept. But just a simple model, simple intuition is that the behavior change in the red curve is less than the other two. The other two has 3 points that their behavior is completely changed. So optimization with a smoother curve is easier. So you select the exponent to make the output of the model, to make the output of this model a positive value. So now we met the first condition, which is the positivity. What happened to the second one? The second one, how easy is the second one? What do you think of? So for the second one, what should we do? We know that this PDF, this is our PDF, must be, the area under curve must be equal to 1. So we can divide it by something like z theta, which is called partition function, and as a result, the resulting, the new p theta of x is normalized. And z theta is this integral. So it seems that the second one can also be met easily. Yes? Yes.
Why the negative?
That's the intuition from the statistical physics. Yeah, because it is equivalent to entropy. When you have the lowest entropy, for example, you have corresponding probability. Yeah, that's the intuition from some other.
Now, would you go to the points? So the red curve is an approximation of p theta.
An approximation of.
Like when p theta is 0, so.
Yeah, it should go to the end. Yeah. It is not exactly 0.
I know, but like from minus 0.10 to 0, the red curve is like increasing to be smooth, but the value of p theta x is constant.
The value of p theta. You mean
The blue curve?
The blue curve?
The blue curve, yes.
You cannot see the changes here. You know, these are non-zero but near 0. And it can be translated in the logarithm. The logarithm can understand those small changes, and you can see them in the red curve. You know, when it is 0, the red curve should be minus infinity. Any question? Yes.
Yeah. So when you have like a model that predicts these p data, how do you actually get the z when you have to integrate over?
Yeah, that's the problem. You cannot get a z, and this is the problem with these models. You cannot calculate z theta easily. Why? Because it is the integral of the output of a very complex neural network. And calculating z theta is intractable, and so although you have a very flexible model, but you have a severe problem here to calculate z theta. And satisfying the second one is, the second property is very hard. And all we talk about is how to mitigate this problem in this energy-based models. This is the most common part. Yes?
So why the function value goes over to 400? Like p theta is the probability.
No, it's unnormalized. That's just the normalization.
Like the probability of unnormalized probability. What is unnormalized probability?
You will see in the energy-based model that you have always unnormalized probability. It means that you have a curve. You have a curve like this. This is unnormalized, but relatively it can provide you that whether x0 is more probable or x1. Because irrespective of the normalization factor, based on this curve, you can understand that x1 is more probable than x0 is more probable than x1. But you do not have the absolute probability for each of them. This is the problem with energy-based model. Because you cannot calculate z theta, and p theta of x, a normalized version, cannot be calculated. You always have unnormalized, yeah. So we have p theta of x, which is always positive, but it is not. It is unnormalized. So one idea is that why do we need normalization? Why do we need normalization? This example can provide you with some intuition. Assume that your data samples are these two lines, and your model is the blue curve. Okay? When maximizing the likelihood of your data set, we know that we sample from the data set. It means that I sample this point, because I do not have any other points. Okay? And then changes my model so that the model give high probability to those points. When the model is not normalized, in other words, it has lots of widgets. What does it mean? It can easily preserve its previous picks and also add 2 picks here, because it is not forced to be normalized. It can assume that this curve is normalized. For example, the area under this curve is 1. When you do not have normalization, it can also provide some likelihood for these 2 points and also preserve its previous peaks. So the area here is more than 1. Why? Because the area in these 2 was 1, but you have some new area here. But on the other hand, you also, to some extent, give probability to data set likelihood. What is the problem with this model? If we accept this model, you do not need normalization anymore. Why you can accept this model? Because this model gives high probability to some points like this. And these are not, it has spurious peaks. Peaks which are not working, which are not provide you with understandable samples. For example, if you train over images, these peaks are on the images which are not understandable. Why? Because the data is not probable here. When you have a limited budget, it means that you have the area to be equal to 1. Then what happens? Then the model is forced to zero the spurious peaks to provide you new peaks in your data samples. Does it make sense how the unit integral works? When you have lots of budget, you can provide some area under curve for data samples, and then you have spurious samples, spurious peaks in your models in these points. So it is not working, because when you sample from your model, you are not confident that you are sampling from this point. You may sample from this point. And this is not understandable point. It is a garbage sample. But when you limit your budget, it means that you must zero out these two peaks to provide some area for your training data samples. So the unit area is very important property for the generative model based on energy based. Does it make sense? Okay. Now we want to know why we use these types of modeling. Although we have lots of different generative models, why do we use the energy-based model? In this presentation, I start with cons and pros because to have some better intuition of the models. The first cons is that assume that you have something, everything is trained, and you have a great generative model. You have a great model that can model the probability for you. What do you think? How I can generate samples using this model? Previously, you can easily input Z into a generator, then you have samples. But how do you think I can generate samples using something like that? Yes.
You can add some variance maybe to the inputs.
What?
You can add some random variance to the
I start with random X.
As you said, X is already random.
Yeah, I start with the random. No, because I do not know how to sample it. Assume that I start with the random variable X and calculate the likelihood. At the output, can this p theta of X provide me with some intuition that how can I change X so that it becomes more probable? Can it give me a direction for X so that if I walk through that direction, then I have a more probable sample?
Yes.
How?
Gradient.
Exactly. It can provide you with some intuition that how you can increase this p theta of X. Because it is a function of X. It can say, so if you want to increase p theta of X, you should go to this direction. The gradients talk about this idea. It gives you the intuition how you can increase or decrease the p theta of X. You want to increase it. So in an iterative way, you can increase the likelihood of that samples by changing the sample. Yeah, does it make sense? In several iterations. You start with a random sample and update your sample so that the likelihood is a large value, so that you are confident that it is coming from a peak of the model distribution. Yes.
So the maximum probability is it's bounded, right? It's bounded to 1. So if it always matches to 1,
Its area is bounded, not its value. Yeah, it's area.
Yeah, it's
involved.
area is bounded. So, I guess what I'm asking is, would you get good variance in the generated samples, or it would just converge to one place?
It converges to one peak, okay? But there are lots of peaks in the generative model, and you will have diversity in your samples. Yeah, you know, it has peaks, but the order of peak is to 10 to the power of minus, for example, 6. This is the value of peak, because the area in the complete space should be equal to 1. Yeah, the probability are of this order. Yeah. Any question? So you see that the generation becomes an optimization. So it's very hard to sample from them. So it is the first cons, that sampling an EBM is very hard. This is the cons. The likelihood calculation is hard. Why? Because it needs that partitioning function. If you do not have the partitioning, you cannot have exact likelihood calculation. You need the partitioning, and in lots of the application, you do not have that exactly. It means that you do not have the likelihood exact. The other cons is that there is no latent representation. There is also almost nothing. There is no latent representation in this setting that we talk about. There are some EBMs, for example, like restricted Boltzmann machine, that can provide you with latent representation. But with this formulation, you cannot see any Z in this architecture. Okay, so in the original, in the simplest case, you do not have any latent representation. But what is the pros? The most important pros is that the only limitation over the architecture is the input-output dimension. It means that it is much more flexible than even the GANs, okay? Because you just need a mapping from RD, this is uppercase D, to R, which can be easily satisfied in different architecture. For example, CNN, RNN, GNN, and also attention-based models. All of them can be used for energy-based models because you want input, you want one real valued output. The input is R dimension D, the output is a real valued number. So there are lots of work in this direction. And you will see that at the end of the EBM, we will transfer to diffusion models as an, it means that starting from EBM, we'll convert to something like diffusion and too. Okay. The second one, I want to talk about the flexibility, you know. Any problem castable as input to a scalar mapping is solvable via EBM. What does it mean? It means, for example, if you have a classification problem, it can be cast as a vector into a value. How? Assume that I want, for example, this classification problem. This is an example from this reference. This reference provides some very well intuition to energy-based models. Please check it. It's very well written. You see, I have a classification problem. How I make it a generative model using EBM? I make a joint vector based on the image and label. And this is my new X vector. Now, if I can train a generative model over these vectors, then I can do classification. How? For example, I have these 4 classes, and an image is input to my system. What do? I start input, calculate the p theta of image with label number 1, calculate it with label number 2 until the end. Label number 2, and each of them is a probability. And then based on the value of these probabilities, I can decide which label is the best label corresponding to image. So I can do image classification easily using the formulation of an EBM. And also you will see some other types of, let's say, modeling using energy-based model, for example, for bounding box detection, for pixel-wise classification, speech tagging, image registration, optical character recognition. All of them can be solved using EBM in something like this. So EBMs are very, very, very flexible, and you can cast different tasks into a setting of an EBM. Okay, any question? So we now, in contrast to the previous generative models that we will generally talk about the models and then about the learning part, now because the bottleneck is sampling, we want to talk about sampling in this part. We know that there is some, for example, a model is trained using some ideas that we will talk about later. And now I want to sample from an EBM. Okay. Any question? Yes.
Did you cover how we can implement the unit volume?
Unit volume?
Yeah.
We generally do not implement it, you know. We just use the unnormalized probability PDF.
So we may have these garbage samples.
No. We will provide some ideas that delete those spurious peaks. Yeah, but we do not generally calculate the partition function. It is very hard.
So having the unit volume necessitates to having all the x's to be able to calculate that integral to normal.
Yeah, if you want to have the exact unit volume, you need to calculate the partition function. But you see that we can even estimate that using some ideas from Monte Carlo estimation. We will have the next presentation.
So we cannot delete those peaks right now. We just have to do some tricks to...
Yeah. Now assume that I use those tools and train a model that delete those peaks, and now I want to sample from an EBM. Okay, we will talk how you will train an EBM. Just now, we want to focus on sampling from an EBM which is not normalized. So you do not need the partition function. It is trained. But the spurious peaks are also eliminated from the model with some tricks that we will talk about later. Now I want to just focus on sampling. Okay? We know that the EBM cannot give you the exact likelihood of a sample, but it can exactly compare whether x1 is more probable or x2. Does it make sense? Do you agree? I can compare the probability of, not the exact value of the probability. I can whether x1 is more probable or x2. Okay. This is just the idea that we talk about. You have a sample xs, and you are given a proposed sample xp. X of proposed, x sample. Now you can check xp is more probable than x1 using this formula. Because the p theta of xp, which is not accessible for us now because we do not have the likelihood, the model likelihood, we just have unnormalized likelihood. You know, if the xp is more probable than xs, then these two relations will be valid, and on the other hand, it means that xp energy is less than xs energy. So if your energy function for xp is less than xs, you can conclude that xp is more probable than xs. So we have the first algorithm to sample, which is Metropolis-Hastening Algorithm. It is a kind of Markov chain Monte Carlo algorithm we do not delve into the details of Markov chain Monte Carlo. We just see some samples of this method. The first one is Metropolis-Hastening Algorithm. That's produce samples from unnormalized distribution. This is the most important property of Metropolis-Hastening algorithm. Yes.
That's like a deep sampling also.
Yeah, it's something like that. But Metropolis-Hastening, the proposal method will be changed. We will see that how you can model the proposal algorithm. Okay, so what is Metropolis-Hastening algorithm? Given an unnormalized PDF, it can give you samples from that PDF. This is the algorithm, what the algorithm do. How is the concept? It initializes with XS randomly. It's you have a random sample. You propose a new candidate based candidate XP, and then accept or reject XP after sufficient number. Accept or reject XP, and after some sufficient iterations, it means that iterating between these two, you will, if you continue your generation, you have samples from P theta of X. It means that I start with XS, some algorithm, some other algorithm propose XP, then I accept or reject. And I have new XS. I think I have a great figure here. Yeah, that's better. Assume I have XS. What happened next? There is some black box here. We do not know the black box. The black box is a proposal method, and this method proposes a new XP. Then what happened next? I estimate the energy of each of these two samples, E theta of XS, E theta of XP, and then based on their energy, I decide to accept or reject XP as a new sample. This accept or reject is such that it guarantees that after sufficient iteration, you have samples from your unnormalized distribution. It means that there are lots of theoretical works here, how to accept, when to accept it or when to reject it. And as a result, if you use the suggested black box in the Metropolis-Hastening algorithm, after enough iterations, you have samples coming from the true data distribution, the normalized data distribution, although you do not have access to the normalized distribution. Okay, does it make sense how it works? This is the Metropolis-Hastening algorithm, and you will see both of the black boxes here. Well, you initialize with x1, and for s equal 1 to t, first you sample xp from a proposal distribution. We know that we can use the gradient as we see before, but in the first algorithm, which is Metropolis-Hastening algorithm, you use another distribution to propose a new sample. Okay? How it proposed a new sample? For example, this is the unnormalized distribution. Assume you are here. This is x1. What happened? You consider a distribution over x1 here. This is a new Gaussian distribution. And then sample from this distribution. This is a normalized distribution, so you can easily sample from it. There is no need to, for example, iterate or something like that. Okay? You sample from this distribution, and we call it XP. This is the proposal. It can be, with a high probability, it is again X1, but we know that it has some changes in comparison to X1. For example, X2 is here, assume. This is X2. Sorry. This is XP. This is proposed, okay? It is dependent on the value of tau. I don't know what is this X. This X is spurious. Yeah. It is based on the tau value. You know, when the tau is large, you have you give high probability and you will escape from x1, and when it is small, you will always come with some proposal new samples near x1. It is dependent on tau, and you will see that changing tau, how it affects the convergence rate of your algorithm. Okay, then what happened? For the proposed sample, you calculate a value of alpha. What is this alpha? This alpha is the ratio of p theta of xp to the p theta of xs times the qxs given xp, qxp given xs. What are each of these elements? Okay, the first one, the first ratio, the ratio of p theta is equivalent to the exponent of energy minus energies. Okay. What happened here? What happened you will see in the next. Just pay attention to the fact that how they are affected this ratio. And also these Q values. It means that you compare whether if xs given xp and q of xp given xs. It means that if you change the proposed point and the sample, what happened to the value of Q? In some distributions, such as Gaussian distributions, they are equal. But you may select some other distributions which are not equal. Just the concept of alpha will be defined next, okay? Then you compute minimum of 1 and this alpha value, and then you sample from U. You sample U from a uniform distribution, and based on the value of U, you accept or reject XP. It is a bit confusing, but now let's focus on the elements of this algorithm. Okay? Yes.
So why Q, XS, even XP, and vice versa are the same?
For the Gaussian, because the Gaussian is just a function of the distance between the points.
So here, on the denominator...
No, I mean for this type of Gaussian, not a Gaussian in general. A Gaussian, it means that it is diagonal and the diagonal elements are equal. Just for this type of Gaussian, sorry. What happened here? Let's focus, assume that the first part is, just focus on the first part. Assume that I select alpha to be p theta of xp or p theta of xs, and I do not want to work with q. Or q is something like Gaussian that it is equal for both states. Okay. Now, when is alpha more than 1? When the proposed sample is more probable than the sample you have. Okay. When the proposed sample is more probable than the sample at your hand, the alpha is greater than 1. Here, the uppercase A is 1. When this part is just equal to, it means that with the probability of A switch, or with it's here. If U is less than A, you switch. If not, you preserve your previous point. Now, for this case, when XP is more probable, what happened? This A equals to 1. So always this term will be satisfied. And you always accept the new sample. Yes? It means that in Metropolis-Hastening Algorithm, when you have a more probable sample, it is not the final algorithm. It has a correction. Okay? So when in the Metropolis-Hastening algorithm, if you assume that alpha is equal to p theta of xp over p theta of xs, then always xs plus 1 is xp if the new point is more probable than previous. What happens using the second term? If there is some, for example, some higher probability given to the proposed sample just because of the Q distribution, it means that the Q distribution is giving higher probability to that point. You do not have always, for example, assume that I select something like this as my Q distribution. Something which is very skewed. Okay, then there may be some, for example, this is xp, this is, for example, xs. Then there may be some problems with the Q distributions giving higher probability to, xs, xp, giving higher probability to the xp because of the proposal distribution. So this term corrects that part. That if Q is, if xp is favorable in terms of Q distributions, then it reduces the value of alpha. You know, if it is favorable in case of Q, it means that this is a large value, this is a small, then you will reduce the value of alpha. Reducing the alpha reduces the chance of accepting the new proposed sample. Why? Because this threshold is reduced. In the marginal case, if this A is 0, you always reject the proposed sample. It is not in application, okay? It is not in practice. But in theory, if alpha is equal to 0, then the large uppercase A is 0, then you always reject the sample. Because this term is always happening. So what happened? You have an alpha value. The alpha precisely look at the likelihood of proposed samples in comparison to the sample at your hand, and also how favorable is the proposed sample in the Q distribution. Then calculate a value of alpha. This value of alpha may be more than 1, then it is clipped to 1, and generate uppercase A. Then based on the value of this A, you better accept or reject the proposed sample. Does it make sense? Yes.
These two distributions, like XS given XP and are two different distributions. Because the mean
functionally they are the same, but the mean, yeah. For example, the mean is once is XP.
The other is different.
Yeah.
So this comparison of dividing these two together, since they are not the same distribution, how does it say whether something is favorable or not?
Yeah, you know, maybe you are thinking about the Gaussian itself. Okay, this is XS. I'm talking about the case we have here, okay? This is XS, and assume that the sample is generated here, XP, XS, XP, okay? The second term compares the probability of this point, probability of XP. It is in the denominator, XP given XS, this is in denominator, and also it's exactly the same, it's my painting problem. Exactly the same variance, they are the same variance. And now this is XP, and this is the Q of XS given XP. In this case, they are exactly the same, okay? But sometimes, like this. For example, this was our XS. The proposal is such that the resulting distribution is here, and you know that when I have this distribution, I am probable that sample from this point. So XP is here. Okay, now what happened? You change the positions. You change the XP and XS. So you have something, maybe for example, it's an exponential distribution. It cannot be negative, something like that. Then the Q of XP given XS is this value, large value, but the Q of XS given XP is this very small value. And it corrects the acceptance. In this case, it is not dependent, this XP selected is not dependent on your unnormalized distribution. It is selected just because the Q give high probability to this XP. So it should be corrected, your acceptance, okay? Does it make sense? Maybe sometimes Q is not working very well. Q give high probability to that point, but that point is not a good point based on your distribution, unnormalized distribution. So, as a result, what do you think in this case? Should I increase alpha or decrease alpha? In this case, exactly this case. What? Decrease. And this formulation decreases because XS given XP is very small, XP given XS is very large, so this value is very small value, so alpha will be decreased, so you, with a lower probability, you accept XP.
So how does this XS or XP have an effect on the distribution, not the Gaussian, like the one that you have plotted?
On the proposal distribution, for example, XS is the something like the mean of the distribution in the case of Gaussian, but in the other distribution you should select the form, you know. But generally this is the case. When you change their value, you can cancel the favorability of the Q distribution for one samples over the other one. It means that this favor distribution is not coming from your unnormalized distribution, it's coming from the Q. And by using this ratio, you correct that value. This correction guarantees that after enough iterations, you have something that is coming from your true data distribution. Yes.
Is there any assumption on Q?
Yes, we'll talk about the assumption on Q. The most important assumption is it should cover all the possible values, that is, your unnormalized distribution is non-zero. Otherwise, you cannot generate samples. Yeah. Any question? Yes.
This procedure, so there's some P, or in this procedure, what's happening, P the, like, some distribution that is occurring in whatever phenomenon you want to model, and then you're modeling it with Q, and you're trying to find a sample from Q that seems like it should be coming from P, or is likely to have come from P.
Yeah, you know, the proposed distribution just randomly selects something around your current point. Then you look at the new point. Okay, this point is more probable based on Q, or it is more probable based on your unnormalized distribution, okay, than XS. Okay, these two factors balance their effect. First part, it balances the effect of the favorability in terms of your unnormalized distribution, which is your objective to sample. The second one normalizes it based on the Q distribution. Whether this new sample is generated just because the proposal distribution gives high probability to that new sample or not. It is not favorable in terms of Q. So there will be an alpha value which is looking both to Q and your unnormalized distribution. And now, based on this alpha value, you select whether to accept the new samples or not. Does it make sense how it works?
But first, during this process, in a later step, will we talk about how to learn Q?
Learn, the Q is not learned, it's selected.
It's selected.
Yeah, we will talk about some options. Yeah.
And I can ask those questions.
There is also another one option here. QX given XS is a normal distribution over around XS. It means that what do you think? What do you have? You have a distribution over XS, a normal distribution. The variance is tau to the power of 2. And now this is the proposal distribution. This distribution, you sample from it. Generally, you have some samples near XS based on the value of tau. And then based on that value, you calculate alpha and then whether select or reject it. But selecting or rejecting have some pulses from the unnormalized distribution. It means that unnormalized distribution decide whether to accept this new sample or not. This is just a proposal distribution. It just proposed samples.
I guess my question was, why do we care about the ratio, or like, so?
The ratio of Q, you mean the P?
I understand why P, because P is like the real distribution we care about.
Yeah.
Q is the thing that's just giving us samples.
Yeah.
Why do we care about the probability in Q?
Yeah, just pay attention to this example, okay? In this example, let me rewrite it here in a more understandable way. Assume that this is, if the proposal distribution is symmetric, then the second part will always be equal to 1 and nothing happens. So just the cases which is not symmetric, such as some exponential family distributions, okay? Assume that XS is here, then XS is here, and then it's determine the form of the proposal distribution, okay? XS determine the form of the proposal distribution, because here, for example, XS determine the form of this Gaussian. Here it's also determine the form of this exponential family. For example, it is the mean of that distribution. We know that when it is skewed, the mean is not the peak. The mean is something on the right. Does it make sense how we select the proposal here, not in the Gaussian case? So what happened in this Q distribution? This is the Q of X. This is the Q of X given XS. I always mistake. This is the Q of, what happened? What do you think? Where it samples from? Because you sample from this distribution. Where you sample from high probability point. So you may sample something from here. Okay? But this sample is sometimes, for example, let me write down a form for, this is the form of the true unnormalized distribution, okay? I want to have something. Assume that this is the unnormalized distribution. This is the unnormalized distribution. What happened here? Although you are near the most important peak of your distribution, because of the proposal distribution, you go somewhere which is not a great point. Although it is again a local peak, but it is not as large as the previous one. Does it make sense? This is the true unnormalized distribution. This is the proposal. Okay? So, what happened here? Not only the true data distribution, let me put it a bit here. You are here. if you have if you change a bit around XP, you will reach the best point based on your true data distribution. But because of the Q distribution you selected, you go to this point. A good algorithm should not accept this XP. Does it make sense? But if you just look to your unnormalized distribution, you will accept it. Why? Because it is higher probability. Do you see? Yes? But when you correct it, you will not accept it. The probability of acceptance will be reduced. Why? Because this is the Q of X given XS. I do not have any other colors, sorry. This is Q of X given XP. So what happened to the correction factor? The correction factor is the ratio between this number and this number. This is the denominator, this is the numerator. So it is a very small value. And decrease the acceptance chance. That makes sense here. Does it make sense? Yes.
And also, I just want to mention, I think that alpha is constructed because, we want to, the MCMC to have detailed balance probability. So when we run the chain for long enough, it will converge to the stationary states.
Yeah, exactly. You always have impose some uncertainty, and in some cases, although the probability in unnormalized case is increased, you do not accept the sum. Yes.
So in some sense, you want to enforce to pick samples quite near the XS.
If you impose that, your convergence rate will be very slow. There is a trade-off. If you increase your variance, if the tau to the power of 2, if you increase your variance, then you make your model to freely select. If you increase this tau value, you make the model to freely select samples with a large distance to your points. You know?
No, because of the factor of those Qs divided by each other.
Yeah.
I'm saying that since as you go farther away, the probability of choosing a sample which is a high probability and you need this correction factor would go also up. So in some sense, you're saying that just be around the XS so you are more sure that the resulting probability that this correction factor is quite...
And also there is another point that many information is gathered in this XP. You cannot escape from XP. There is information in this XP. It means that for example, in a gradient descent, you make the step size very large. It means that you escape maybe from the local minimum that you were near the local minimum. I just want to make sure that you understand this example because it's very important to have the concept that YQ and YP, both of them affect that alpha value. If it is not clear yet, we can talk about it in the next session. Do not worry. We will talk about this example and this algorithm in the next session. Thank you very much for coming. Have a great day.